think it's working now. Cool. So, welcome back to week 9 of concrete. So, today I'm going to run through serviceability, and I'll also, hopefully if I have time at the end, talk about how designing slabs works, okay? So everything that you've kind of learned so far in this course is in relation to beams and beam design. So let me kind of give you an overview of that, right? So I'll just go down to the course content and give you a quick recap. So in previous weeks, we learned about flexure and flexural design. We learned about shear, and now we're going to learn about serviceability. Okay, so these are kind of design actions, right? So flexure, you're designing for like a bending moment, and you have to make sure that it's less than your capacity that your beam can take, right? For shear, we do a similar thing, except it's in terms of a shear capacity versus your shear force at your critical location, right? Serviceability is similar, and I'll run through this in more depth in a second. But the idea is the deflection that your beam has to, like the amount of deflection your beam does. So just a recap of solid mechanics. If you have like a uniformly distributed load on a simply supported beam, the deflected shape of your beam will look something like this, where the max deflection will be peaked at the middle, right? So this deflection amount has to be less than some kind of limit, all right? So rather than a force or a moment, you're designing for kind of like a millimeter value, like a geometric limitation, right? So this is in millimeters and this is in millimeters, okay? So, and we've been learning all of this in the context of beams, but what I'll briefly mention towards the end of this lesson is how we interpret this for different flexural members or different like structural members built out of reinforced concrete. So one of those is a slab and the other is a column, okay, which we'll talk about more in depth next week. So that's kind of how this course is structured. You've got your different design actions and limits, and we learn about that in the context of beams, and then later we kind of have these more applied topics in terms of here's like the start to finish design of a slab or a column, for example. Okay, cool. So let's talk about serviceability. So this is kind of like a different philosophy when designing things, right? As a structural engineer. So there's this guideline, or like the standard, right, called 1170.0, and there's this thing that they talk about in it called limit state design. And what limit state design is Australia's specific version of factor of safety, okay? So I'll just quickly recap on how it works, right? So if you've got a scaffolding system, for example, and you have people on it, right, workers, and each of these workers weighs 100 kilos. This scaffolding system, if you design it to just resist 300 kilos, it'll probably break for various reasons, right? For example, if these workers jump up and down, right, then this is going to be a higher equivalent static load than how much they actually weigh. Another reason could be like the assembly of the structure itself is poor, right? So you could be missing bolts or something like that. That could reduce the capacity. And so we have to apply a factor of safety of some sort, okay? And this is basically the concept of over-engineering a little bit. In other words, you would basically make the structure stronger than what you predict like the loads to be. So the limit state design is just the philosophy that Australia adopts for this kind of engineering over-designing. Okay, so kind of how we've been thinking about it this entire time is through the lens of ultimate limit state design. So ultimate limit state design is also called strength-based design or safety or like preventing collapse. And you should be pretty familiar with this now because that's kind of what we've been doing weeks 5 through to 8, where we're just comparing like you know, the ultimate capacity of something. In other words, how strong it is in like the worst case scenario, basically, right? Okay, so why this is different to serviceability is serviceability is not dealing with collapsed loads. It's not dealing with like the worst case scenario. It's dealing with everyday loading. So this is to do with everyday load. Another word that you'll hear a lot is service loads, okay? So yeah, like how can we design our structural members to satisfy like everyday use? And one of the ways that you can do that is through the lens of deflection. So deflection is basically saying, based on these everyday service loads, how can we design our beam to not sag a certain amount, okay, or deflect a certain amount, okay? And I'll give you another quick explanation on kind of how we exaggerate or under-exaggerate these loads. So at this point, you're probably pretty familiar with the concept of a dead load and a live load. So under the philosophy of strength-based design, you know that we have these exaggeration factors like 1.35 or 1.2 for dead load, and we also have exaggeration factors for live load, right? Under service loads, these are either basically unfactored or under-exaggerated in some way. So service loading for dead load is just the dead load that you predict. And then the live load for service is something in the ballpark of, 0.7, 0.4. Okay, so these numbers you'll see in generally for the case of the short-term load factor and the long-term load factor for live loads. Okay, so what does this mean? Firstly, it's an under-exaggeration of the live load. And I'll give you a little analogy. So in the civil building, for example, or any of the buildings, most of the buildings in UNSW, you've got like an elevator or whatever. And this elevator can fit like however many people in it. And it'll even have like a little sign which says this elevator can take 13 people's capacity or something like that, right? So that is based on this ultimate or strength-based calculation, okay? But for service loading, right, so I just want to quickly draw your attention to the fact that these people represent the live load, okay? For service loading, in the short term, so for example, if you were just to calculate it today, right, we might say that it's only at 70% capacity, right, for example, right? So instead of reaching, say, the queue was like for 5 people or something like that, okay, fitting in the elevator, right, we say that like, okay, I don't know, it's a bad example, 10, okay, we say that like, okay, today we measured it and only 7 people got into the elevator at a time or something like that, right? So that's short term. In the long term, it's saying like over a long stretch of time, what's like the average kind of loading? Okay, so for example, yeah, again, if we're accounting for 10 people, it's saying that like, so because UNSW is like a school, right? And there's like these holiday periods, right? So over a long stretch of time, there could be long stretches of time where no one's using the elevator, okay? And so when we're thinking of this in the context of deflection, for a beam, it's saying that it gives the beam a little bit of time to restore the sagging, right? For example, so that's like long term, okay? Yes, okay, so that's ultimate and service limit state design and the kind of philosophies that we adopt. That's just basically saying those are the ultimate kind of actions that we've looked at. Okay, and now you'll see here, serviceability is basically you're limiting the deflections versus some kind of limit. And the limit is based on this concept of curvature. So let me give you another analogy. Yes, this is why people subscribe to Sigma lectures. Okay, so imagine you have like a cucumber or something, right? The ends of the cucumber are like perpendicular, right? Oh, sorry. Okay. you draw a line from like the ends of the cucumber, right? It will have like these parallel lines that never meet each other, okay? Whereas for like a banana, for example, right? I'm gonna draw two bananas, right? You've got, if we do the same thing, right? We can have different levels of this concept called curvature, right? So you can tell that this banana on the right is more curved than the banana in the middle, which is more curved than this cucumber, right? And the way that we measure curvature, I'm trying not to laugh while saying all this shit. Okay. The way that we measure curvature is with this Greek letter kappa, right? And this is basically equal to 1 over the radius of curvature. Okay, so this is an easier way to kind of interpret it, right? So the idea is, let's say we measure from this kind of imaginary point to the neutral axis of the banana, okay? That's basically the radius of curvature. So that's one way you can think about it, right? So if you have a larger radius of curvature, you have a lower curvature, right? Whereas conversely, if you have a lower radius of curvature, you have a higher curvature, okay? So if you have a higher K, it means this thing's more curved. Yeah, so there's kind of an inverse proportionality between these two concepts. Okay, so now let's ditch the vegetables and fruit and whatever and talk about a beam, right? What this is saying is we want to limit the curvature of these beams. So these are simply supported beams. We want to limit the curvature of these beams in some way. Okay, so if you have a beam that is, okay, you know what? One second. Just frozen? Okay, no. I'm going to copy this. So if this beam's original length, right, is 5 meters, for example, whereas this beam's original length is 10 meters, okay, but they have the same curvature, right? You can see that this has the same shape when we look at it. It's not fair to basically compare their deflection, right? So that's the deflection there, and that's the deflection there. And let's just say in the first case, this deflected 1 mil, and this deflected 2 mils, right? Because it's double the length, right? Just for the sake of argument, if everything got scaled up. So the idea is that the limit of our deflection has to be based on the curvature, right? In other words, it has to be a function of the length of your overall member, okay? And so when this is given in the code, this is saying that our limits are based on your length divided by some constant that you put in the fraction, okay? So for the case of simply supported beams or continuous beams, you take the length and you divide it by 250. And for the sake, in the case of cantilevers, it's divided by 125, okay? So yeah, and this is basically, so LEF, right, is like an effective span. So let me help you, I'll draw a little diagram for this, right? So if you have a concrete frame which has columns and beams, right? And the distance between the columns, that is just air, right? That's the net length, okay? And the depth of the beam is d. The idea is the center to center length, right, is here to here. So this is from the center of this column to the center of this column. And then you take whichever is smaller, right? You take the clear span plus the depth, right? So you have to do that plus that versus just center to center. So you take the smaller one between those, and that's your effective span. Okay, so you take that value and you divide it by either 250 or 125. Or sometimes it's overwritten in the question. So if you're reading the question and it tells you take a limit of L on 350, LEF on 350, then that's the limit that you take. Okay. Any questions so far? Okay. So just give you an idea of where you can expect to see the max deflection for various cases, right, of like supporting. So for a simply supported beam, the max deflection will be in the middle. For a cantilever, the max deflection will be at the free end. And for a continuous beam, they'll be approximately in the middle as well, okay? So that's what the code does. Even though the true like maximum deflection point is actually for an end span slightly offset from the middle, the code simplifies it and just says we're checking for this spot right in the middle of the end span. Okay, so moment curvature relationship, this is just a little recap from solid mechanics of how we can relate or like get the deflection formula. So if you imagine a beam and the distance you move along the beam is x. Okay, so we're basically making an xy graph, right? And instead of y, let's just chuck that as deflection, right? And we're saying as well that the positive direction is going down. So deflection is mapped downwards. And what we can, and we basically can get the parabola function for the deflection or the deflected shape of a beam using this kind of logic that I'm about to explain, right? So this is specifically for a uniformly distributed load. Okay, so you've got a UDL of W, right, being applied on this beam. So from geometry, this is saying that if you get the deflection and you differentiate it, you get something called the slope, which makes sense because the slope is just the instantaneous slope at any point along your beam. So for example, the slope gets lower and lower up until here where you've got zero slope, and then here, yeah, it goes the other way. So that's the slope. And the curvature is the second derivative of deflection. Okay, so that's going to be our definition of it. What I was showing you earlier was just a way to basically easily visualize how curvature works, but the official, like the actual definition, oh sorry, this is like actually the definition as well, but this is like the less intuitive definition. It's a second derivative of deflection. Okay, and then from equilibrium, in other words, if you take this load on the beam and you want to basically draw its shear force diagram and its bending moment diagram, okay? The moment, right, if you differentiate that bending moment diagram, right, that one, you get the shear, okay? And then if you differentiate the shear, you get the load, okay? So that's kind of how those are all related to each other in terms of their derivatives, right? And the other thing is that moment and curvature are actually related to each other through your flexural stiffness. Okay, so flexural stiffness has two components. It has the elastic modulus, which is basically a material measure of stiffness in the elastic region. And then you have moment of inertia, and moment of inertia is basically your shape stiffness, specifically in bending. Okay, so these are two kind of like stiffness quantities that are multiplied together, and that gives you your flexural stiffness. So basically M is related through to kappa through EI. Anyway, so curvature ends up being the link between geometry and equilibrium. And what happens is you can see that W is related to delta, and it's also related through a polynomial of order 4 for length. So what do I mean by that? Okay, so if you look at the deflection formula for a simply supported beam with a uniformly distributed load, it looks something like this, right? So what I'm trying to say is that delta is related to the length with a order of 4, right? A polynomial order of 4. Okay, and that comes from 4 steps of differentiating, right, between those two things. Oh, that and W, I should say. Anyway, you kind of get the idea. Anyway, so that's where all this comes from. Okay, so that's the deflection of an elastic, like generic elastic material. Okay, so I'll give you an example. If you have a steel beam, right, and you didn't really learn this in steels because for whatever reason at UNSW, we don't do serviceability design in steel structures. But you have a steel beam, and basically if you apply like service loads to it, right, it will deflect like so. And the material curve for steel looks something like this, right? And it's going to be equal in tension and compression. It's going to be mirrored. But all of our service loads, right, are not going to be related to yielding. It's the loads and stresses that happen before yielding. Okay, so essentially your steel beam, in terms of deflection, behaves elastically. Okay, so when you load it, it'll deflect a certain amount, like you can see here. And if you get rid of that load, it basically springs back elastically. And that's kind of what elastic deflection is, okay? So steel would be an example of something that you would treat with elastic deflection, and that's pretty much your only consideration. For concrete or reinforced concrete, there's kind of two things that make it more complicated than that, okay? The first thing is cracking, right? So just to recap on that, I think in week 5 we talked about 3 stages, right, for concrete, which has like increasing moment applied to it. Okay, so this is 3 stages of flexure. So if you have a concrete section let's do singly reinforced, boom, boom, boom. That its neutral axis will be somewhere down here. Okay, and then in the second stage, what happens is the neutral axis will move up because all of this concrete below the neutral axis gets cracked. Okay, and then in the third stage, which is what our ultimate flexural stage is based on, it moves up even more. The neutral axis will move up even more, and then there'll be a little bit of like non-linear material behavior for the concrete. Okay. So basically, when we're dealing with serviceability, we're operating in this kind of region. So between the uncracked stage and the cracked stage, and both stages are elastic, right? But concrete can crack and still be elastic. Okay. So we have to deal with cracking. Okay, so the idea is we're going to work out something called the moment of inertia, the effective moment of inertia, right? And it's going to be a linear interpolation between these 2 stages. So what I mean, in the first stage, the moment of inertia is the gross moment of inertia or the uncracked moment of inertia, whereas in the second stage, that's your cracked moment of inertia. So basically, your effective moment of inertia is some value in between those 2, okay? Anyway, so cracking will change what I is in this formula. So this formula is that deflection formula I mentioned a second ago. And the other thing that we have to account for the case of reinforced concrete, is time effects, so creeping over time. So steel doesn't do this, but concrete does this. It basically will, as you load it, right? As you load it, right? So that's a beam. And you apply like a constant load and you don't move it over a long period of time, let's say 10 years, it will actually sag more than the short-term loading. Okay, so you apply, if there's a beam and you put a bunch of bricks on it, okay, over 10 years, and you don't touch those bricks, it still will sag more. Okay, so that's creeping. So how we deal with this in serviceability and in this calculation for deflection is we have to modify W, right, to account for like long-term creeping effects, basically, right? So we increase essentially the distributed load. Okay, so let me break these down a bit further. Okay, so for cracking, how it works basically is you have a concrete beam and it's in flexure, And what happens is these cracks will start to form where there's like a high bending moment. So near the middle of a simply supported beam, right? And I'm going to draw this in 3D. So if I took a cross section right here, what I've drawn in purple is the area of concrete that we take the stiffness of. So that's above the neutral axis. That's a crack section, right? Okay, and then over here, in fact, the concrete's not cracked, right? So some parts of this concrete beam are cracked and some parts aren't. Okay, so that's the first thing. And another thing you got to realize is between these cracks along the beam, we actually have uncracked sections. Okay, so just to really illustrate that point, all right, say at this spot here, we have a cracked section. This spot here, we have a cracked section, but in between, we have an uncracked section, right? And so the idea is the concrete can still carry tension below the neutral axis in certain spots, okay? So that's one thing. And what we're going to do with IEF is find, it's kind of like a combination of two things, right? The first thing is it's basically saying that these cracks might not actually go up to the neutral axis in reality, okay, depending on the amount of curvature that the beam's experiencing / flexure. It might be something more like this, for example. And so, yeah, like conservatively, we took everything below the neutral axis as being in tension and not working, but even some bits in tension can contribute to the stiffness, right, for the case between stage 1 and 2 for the reinforced concrete. And so that's basically what this is, right? That's saying that not everything below the neutral axis is ineffective, okay? That's one thing. The other thing is you'll see something called IEF average, right, at a later stage, right? So IEF is referring to the fact that you can have portions of concrete which are effective in tension, and then IEF average is basically saying along the whole beam, if you took a bunch of samples, right, what would be the effective stiffness of the cross section, you know, like, anyway, so like this portion over here, which doesn't have any cracks, can contribute to the stiffness more than this portion which does have a crack, for example. Okay, so there's other ways to look at it. Here's a graph which is moment versus curvature. So as I mentioned before, moment and curvature are related to each other through EI. So on this graph, the slope is EIG, so this is when it's uncracked. The moment that the concrete cracks, basically this number drops, right? And the slope will change. And so there's this basically sudden jump if we assume that this portion is uncracked and then this portion is cracked, like so, okay? There'd be this sudden jump, right, at M cracked. Okay, so M cracked is a capacity value, right? So if the service bending moment is greater than M cracked, what happens is, like the beam cracks, right? Whatever. But what we're doing is basically with IEF, it helps to smooth out this curve, right? So the idea is when your beam cracks, it loses a lot of stiffness straight away, but not all of its stiffness is reduced down to I cracked, right? It will have this gradual change. Okay, so that's what the formulas do. Here's a little diagram of what I was trying to describe earlier, where what I was drawing a second ago, these are primary cracks. Okay, so primary cracks form along the length of the beam, and the concrete can actually still carry tension in the regions between the cracks. But once secondary cracks form, which is what happens when more and more bending moment is applied, it basically like subdivides the area that the concrete can carry tension. And anyway, so this is called tension stiffening. It's basically saying that the concrete can still carry some of its, like still contribute in tension. Okay. Anyway, so you can look through this more if you like, but that's where this comes from. Okay, the second effect is the creeping effect, right? So as I mentioned before, the creeping effect, the way that we kind of apply it, right, from the standards is by modifying W, right? Modifying the load. Okay, so think about the deflection of this beam over some period of time. Okay, so there's going to be the total deflection, which is the sum of your short-term deflection plus your long-term deflection. Okay, so this makes more sense once I do a question. And what I'll do is basically in these few pages, so between page, what's this one, 10 to, from page 10 to 16, these are like my step-by-step notes on how to do serviceability questions. So what I'll do is I just have the question here that we're actually going to run through. And on the other screen, which is now signed out, I'll pull up the step-by-step and we'll follow along, right? Okay. So here is the question, right, that we're going to do first. So we're going to simply support a beam, and it's got a rectangular cross-section. And for this particular question, we're given the section size, okay? So for the next question, what you'll see is we're not given the section size, and we have to design the concrete's depth and width and stuff. But for this particular question, we're given a set size, and it's basically asking us to calculate the deflection based on this cross-section. Okay, so it says to calculate the short and long-term deflection for the beam that's shown. Take FC is 32 MPa. The yield strength of the steel is 500. Phi S is 0.7, phi L as 0.4. And this is called the short-term, it's like the shrinkage strain, basically. I'll explain that more in a bit. It's a shrinkage strain. Okay. The other thing is we've got this simply supported beam, and it's got two types of loads on it, right? It's got your uniformly distributed load, and it's got a point load applied in the middle, right? And the whole thing is 6,000 mil long. So the dead load, but yeah, basically the point load and the distributed load have a dead load portion and a live load portion, okay? So that's all written there. And we're told the steel area as well. So basically the first step, or rather I've written it as step 0, is, and you don't like literally need to like write down the step, which is why I've wrote it as step 0, but you need to look at it, you need to look at the problem and try to figure out how many cross sections we need to analyze, okay? So in our case, we only need to analyze one cross section, which will be the cross section in the middle, okay? And so why is this different to other cases, right? So if you focus on the screen on the left, right, you can see all the cases that I've listed out. So when you have a single span, like a simply supported beam or a cantilever, you only take one cross section each, right? So you're trying to take the cross section at points which it's cracked, like it's experiencing flexural cracks. So for a simply supported beam, the flexural cracks will appear in the middle. For a cantilever, it will appear at the support, okay? Because that's the point of max bending moment. Okay, so that's where the tension cracks will form, okay? When you are dealing with a continuous beam, it will be different for the case of an end span and an interior span. So what I've drawn here is a 3-span continuous beam, which just means it's got 3 different lengths between 4 supports. So an end span basically has one side that is continuous, and an interior span has 2 sides which are continuous, right? And so for an end span, basically the stiffness, there's a contribution of stiffness. There's basically cracking that's going to happen in the middle as well as at the support, right? And so your effective average stiffness is going to be a 50-50 contribution from the middle and from the right-hand side. So for the case of an interior span, you take 50% of the contribution from the middle and then 25% from either side, right? And that's going to be your effective average stiffness. Okay, so that's where it's going, but the reason why it's step 0 is before you even start your analysis, you have to basically figure out how you're going to do the question. And so that's the first step. Okay, so now we're going to do, we're going to calculate the serviceability factored loads, right? So as I mentioned before, this is not the same thing as our ultimate case. So you know how for our ultimate, when we're doing like strength design, basically, you do something like this. You go 1.2G plus 1.5Q and whatever. We're not going to do that, okay? So that's different to what we're doing. We're going to do a different load combination, and we'll start with the short-term load combination. I'll tell you why later. So we want to find the short-term load for both the distributed load and the point load, and we want to calculate these separately. Okay, so for... I'm going to scroll to the right page. Okay, so for WG, we plug in 10 kilonewtons per meter for the dead load, and then 8 kilonewtons per meter for the live load. And we're told in the question that phi s is 0.7. Okay, so phi s is usually 0.7, like for the case of offices, residential buildings, retail, and parking. For other cases, right, it's going to be 1, okay? But in most of these questions for suspended floors and whatever, it's going to be 0.7. Okay, when we calculate that, we get 15.6 kilonewtons per meter. Okay, and then for the point load, right, these are in different units, so we want to keep these separate. It's a different unit and it's a different shape as well. Okay, but it's just it's the same phi s factor, right? It's still 0.7 for both. Okay, and then so your short-term load 65 kilonewtons. Okay, so once we know what the service loads are, let me scroll down on this. That's method 2. What we're going to do is we're going to find the service load at the section that we're interested in. So as we did in step 0, we need to look at the middle of the beam, right? So we're going to find what the service bending moment is in the middle of the beam, okay? So what we're going to do is we're going to basically apply superposition. So these are the bending moment diagrams, right? So what you can see in purple here is a bending moment diagram, and this is a bending moment diagram, right? So what we're saying is that this parabola plus the triangle, right, is going to give us this kind of mixed triangle parabola thing, right? And when you add the bending moments together, right, you'll get the bending moment when you apply both the loads, right? So you add the shapes together, basically. Okay, and then these individually have formulas, right? So for the case of a simply supported beam with a uniformly distributed load, you go WL squared on 8, and W was our service load, our short-term service load, and L was 6. You square that, you divide it by 8, you get this. For the service load, for the bending moment due to the point load, you go PL on 4, you go 65 as the point load, you go 6 as the length, you divide that by 4, and then you get this. Okay, and then you basically add those together, right? Add those two numbers together, and you get this, okay, as your bending moments, right, in the middle. So that's those two numbers added together. Okay, next we find the uncracked stiffness, okay? So what you can see on the left screen there, that's what we are going to do in the next question when we have a continuous beam, okay? It looks really annoying, but like it's actually not bad. Okay, so we're doing something called method 1. This is just like my naming convention in my notes, but method 1 is when our section size is known. So that's the case of our question. We're given what depth and width and stuff we're dealing with. So we're just going to continue with these steps. For the next question, we're going to do method 2, which is like a preliminary sizing kind of thing. And you skip over to step 4. So here's what you would do for the case of when you know what the section's dimensions are and stuff, okay? you have to find the uncracked, the uncracked stage stiffness basically. And yeah, this is like the formula, but I'll tell you how to do it. So first you got to find the elastic modulus of the concrete, and this is a function of the compressive strength of the concrete, right? And it's from this table. So for the modular ratio method, we need to divide the stiffness of the steel, or the elastic modulus of the steel, over the elastic modulus of the concrete, right? And one sec. Yeah, basically this gives us 6.64, and then the workshop rounds it to 7 for some reason. I wouldn't recommend doing this in your finals. It feels a bit like wishy-washy to do. So I would just, I mean, you can round it to 1 decimal place if you want, but I wouldn't round it to 0 decimal places. You know what I mean? Okay. Anyway, so the workshop takes it as 7 for n, and so n minus 1 is going to be 6. And if you remember the modular ratio method, we're going to use 6 as the modular ratio, or as like n minus 1, in front of all the terms for the steel, okay? All right, so for the concrete, right? So this concrete rectangle, we want to find the centroid, right, for this shape. And so we take the rectangle, right, which is 600 mil deep. So D is equal to 600. And it's 400 wide. Okay, so B is 400. And then the middle of that, right, the depth to the middle is going to be 300 mil, or 600 divided by 2. So here I've written as 600 divided by 2. And we're going to add on n minus 1. Okay, n minus 1, that's also n minus 1, times the area of the compressive steel. So the compressive steel was this one over here. And then we multiply it by the depth, right, which is 60. And then we're also dealing with the tensile steel, all right, and then that is 540, okay? And then on the bottom of the fraction, it's just everything, it's all the area terms basically added together. Okay, so it's the sum of the areas of the different shapes. Okay, so this gives us a depth to the neutral axis of 304.2. Right, and then for the moment of inertia, the calculation is basically you get the, you go BD cubed on 12, so that accounts for the concrete rectangle. And then you do this parallel axis theorem shift. So what that means, right, is you get the area and you multiply it by the shift distance squared. Okay, so that's the area and that's the shift distance, right? So the shift distance of the concrete is going to be the depth to the neutral axis, subtract by the depth to the middle of the concrete. Okay, so in orange there, that's the depth to the middle of the concrete, and the neutral axis is roughly here. So NA, where basically that's our shift distance, right? And so that's the value in here, and we have to make sure we square it. Okay, don't forget to square it. Okay, so that's the shift distance for the concrete. Now we shift the steel as well. Okay, so again, we get the area, right, which is n minus 1 multiplied by the area of the steel. And then we're to work out the shift distance. Every time you need the depth to the neutral axis as one kind of distance, and then the other one is the depth, right? So that's dn minus 60 for the case of the compressive steel. So we're now taking this as the shift distance for the compressive steel. And then here is what we're going to do for the shift distance for the tensile steel, right? So that's the first case, and that's the second case. Okay, so now we're able to type this into our calculator, right? And we get the uncracked elastic, what's it called? Uncracked moment of inertia. Far out, okay. Okay, so next we want to find M cracked. Okay, so if I scroll through my notes, right? Step 2A is what we just did. And then step 2B, finding M cracked requires a bunch of sub-steps, okay? So I think in the week 5 workshop, some of the questions said like calculate the cracking moment or whatever, but we have like a little bit of an extra step that we need to incorporate to what you learned in week 5. So when we're calculating M cracked for this week's content, you have to basically account for the concrete shrinkage. Okay, so I'll explain that in a bit. One sec. Okay, so we have to calculate two values, right? PW and PCW. So PW is a reinforcement ratio, and it's a tensile steel reinforcement ratio. PCW is the compressive steel reinforcement ratio. Okay, so if you want to visualize it, what PW is basically saying we take the area of the tensile steel and we divide it by the orange rectangle. Okay, so it's not the entire depth that you're multiplying by the width, it's just the effective depth. Okay, and this will give you the tensile steel ratio. So if you do 1350 for your tensile steel, you do 400 for your web width, and then 540 for your effective depth. This gives you a ratio of 0.0063. Okay, and then doing the same thing for the compressive steel, except you plug in area is equal to 620, and then the same denominator, you get 0.0029 for PCW. So that's the compressive steel reinforcement ratio. Okay, any questions so far? Cool. Okay, so it's going to come into play in this next step. So this is called the stress due to concrete shrinkage. Okay, the tensile stress due to concrete shrinkage. So it follows this formula where you get the elastic modulus of the steel, and then you get the shrinkage strain due to the concrete, and this term in here is basically saying the long-term shrinkage strain, and this is saying that it's approximately equal to the short-term shrinkage strain. Okay, and we're told that both of these are equal in this question, and it's 800, and you're going to see 800 mu, right? But this is nothing to do with what you learned in Eng 1300 to do with, like, you know, static friction or whatever. This mu is referring to microns or micros or whatever. So when you see mu in the context of strain, it's basically saying 10 to the minus 6. Okay, and remember, strain is unitless, so it's not in terms of millimeters or whatever, it's a unitless amount. Okay, and then you basically sub in your values for PW and PCW, like so. Okay, and then you get this value, you get 1.63 MPa, and you should be getting a number in the ballpark of 1 to 2 MPa. If you're getting something way lower or way higher, you need to check your units. For example, if you didn't do 10 to the minus 6, you might get like 1 million MPa or something crazy like that, okay? So what does this number physically mean? So if you pour a concrete beam, right, and imagine this is formwork, and then the concrete's wet, and then over time it's going to cure and dry. The idea is this drying process induces tensile stresses because the concrete is shrinking, and it wants to pull away from itself, basically, right? And so we can quantify that amount of shrinkage as this, basically, right? The tensile shrinkage stress, okay? And remember, this is based on the ratio of your compressive and tensile steel, right? So this is basically saying you have less tensile shrinkage stress if you have more compressive steel. So I remember someone asked me in like week 5 or something like that, what's the purpose of compressive reinforcement? We can actually go over now pretty much all the reasons why we have compressive reinforcement, okay? So compressive reinforcement is really useful, right? Because if you just have singly reinforced concrete, compared to the case of singly reinforced concrete, having tensile reo is good for Well, firstly, you know what? One sec. I'll draw both cases, okay? So your neutral axis, right, will be brought up if you have compressive reinforcement. That's for one, okay? So I'm going to exaggerate it a little bit, but it brings up your neutral axis, right? And what this is going to do is when you're doing force equilibrium, like so, right? Well, it's also going to add, right? Anyway, so basically if you, how do I say this? So that's your strain, let's say. That's your strain. Okay. If you have your neutral axis further away, what happens is the tensile reinforcement basically contributes more force. Okay, so this is, you have to visualize this part being drawn in terms of force. Sorry, not force, actually. Okay, so bad explanation. The idea is there'll be a larger lever arm to the neutral axis, and so this is going to give you more moment capacity. So that's one. The second thing is it's going to increase your ductility. So adding compressive reinforcement, there's like your Ku factor, and it's dO over dN, right? And so, or maybe it's the other way around, sorry. And so if dN decreases, right, because this distance is decreased, if that decreases, that's good, because the lower Ku is, the more ductile your section is. So it adds ductility and increases your moment capacity, right? So that's two things it does in flexure. What it does in shear, right, which we went over last week, is it gives you something to wrap your stirrups around, right? So that's pretty important. And then in this topic, it has two uses as well. It will reduce your shrinkage stress, right? And it will also, later you'll see something called KCS, which is a shrinkage, creep shrinkage factor, right? And basically it exaggerates your long-term deflection, right? It will decrease this if you have compressive reinforcement. So compressive reinforcement does about 5 or 6 different things, right? Incredibly useful. Okay, sorry, tangent. Okay, I'm kind of going over time. Okay, sorry, so I'll keep going until the end of this question, and then I'll give you a break. I know it's probably feels like it's been forever, and it's gonna go on for a little longer. So, okay, what is Z? And specifically, what is ZT? So Z stands for your elastic section modulus, which might sound familiar if you did steels last term, right? But if you haven't done steels, then you may not have seen this before. It basically follows a formula. Okay. If you had a rectangle of a solid, right? A generic, let's say this is made out of steel. The way that you'd calculate the Z is by getting the moment of inertia and dividing it by d on 2, okay? And the reason is because if you just had a single rectangle, your neutral axis is located at a distance of d on 2, okay? So if I were to do the stress distribution, and it's elastic, right? Basically, it's even on both sides, right? So that's the case for if you had just a rectangle. However, what happens for us, right, for an uncracked section, is that our neutral axis is shifted slightly towards the tensile steel, and then we're no longer located at d on 2, okay? We're no longer located at d on 2. It's going to look something more like this, okay? Oops. And so what we need to do instead is you're going to have two values, right? You're going to have the depth of the neutral axis from the side in tension and the side in compression. So we know that from the side in compression to the neutral axis, we call that dn. And the overall depth of our shape, let's just still call that d. This remaining distance is called d minus dn, right? Because it's the remaining depth, right? There to there. And this is basically the depth to the neutral axis from tension, okay? In other words, the stress distribution will look something like this. I'm going to exaggerate it a bit, like this. And this is going to be the stress that causes fracture, basically. It's going to cause your beam to crack. So it has to be from the tension side. And the way that we measure that is by chucking d minus dn on the bottom of this fraction. Okay, so this is zt. So now it's imbalanced, right? So t refers to tension in this case. Sometimes you see zt referring to like top side and bottom side. Sometimes you see it like zb. That's referring to like the elastic section modulus from the bottom side. But in this case, it's talking about tension. Okay, so this is the fracture stress, and we have a measurement for this in terms of the strength. It's called F-CT.F. Okay, so CT.F is the concrete's tension strength in flexure. Okay, so F stands for flexure. Right. So when we're experiencing tension and compression, this like force couple, this is the tensile strength. And it has a empirical, that's bad. Okay. It has an approximation in AS3600, and it's equal to this, right? Which we were learning about in week 4. So 0.6 square root F-C, that's the stress which is going to fracture the concrete, right? Which we'll get to in the next step. So basically, let's calculate Z for now. Okay, we just chuck in the uncracked moment of inertia, and we chuck in D is equal to 600, and we chuck in depth to neutral axis. This is the uncracked stages depth to the neutral axis, by the way, giving us this. Okay. Okay, so now, if we want to calculate the cracking moment, what we do is we need to multiply this elastic section modulus by the fracture stress, right? Okay, so we chuck that in like so. But then here, we're going to plug in this, right? As I mentioned a second ago. And F-C was given to us as 32 MPa. However, what we're going to do is we're going to subtract off the stress, which is caused by shrinkage, right? The shrinkage stress, the shrinkage tensile stress. And that was 1.63. And the idea is if you have tensile stresses, it's going to cause your beam to fracture sooner than you expect. So in other words, it's basically going to fracture here instead. Okay, so that shift distance is, did I click something? It's frozen. Okay, that shift distance from here to here is 1.63. Okay, so it's actually going to crack here. Okay, at that stress. Okay, so this gives us 47.1 times 10 to the 6 Newton millimeters. And if we convert this to kilonewton meters, we get this. At a later stage, when you're storing this on your calculator, because this topic, and when you're doing it in the finals, is going to be just a bunch of storing values on your calculator and then putting these stored values into fractions. When you're storing this on your calculator, you want to store it in terms of kilonewton meters, and I'll tell you why later. Or, as in, that's the way that I prefer to do it. But you can, yeah, that's like a little tip. I'll explain why that is in a bit. Okay. The next step is we need to check if the section cracks. Basically, if our section doesn't crack, we don't need to calculate the moment of inertia for a crack section. Okay. So we do the check first. Okay, so for our particular case, we calculated the service bending moment, which was this, and it's greater than the cracking moment, which is what we just calculated. And so since this number is bigger than this number, it means the beam is cracked, and we need to calculate the cracked moment of inertia, okay, the stage 2 moment of inertia. So it follows a very similar kind of logic to stage 1, except we change a few things, okay? So the first thing we change is when we're doing, sorry, and all of this is ineffective. So when we're calculating this concrete what's the word? This concrete block and its size, right? It goes from, previously it was 600, right, as the depth, and now it's going to be equal to our depth to the neutral axis, okay? So we're gonna have dn there, and then we're gonna multiply it by the width, which is 400, which stays the same. And then the middle of this variable kind of distance is gonna be dn on 2, okay? So that's dn on 2 there. Okay, and then we're gonna add on the shift. No, it's not the shift distance. Sorry, the contribution to the centroid of the tensile steel as well as the compressive steel, which doesn't change from before, except for the fact that the tensile steel will now just be doing. We'll be using an a modular ratio of 7 rather than 6. Okay, so this was n-1, and for the tension steel, it's just n. Okay, and then divide by the area, okay, of everything. Okay, so dn is going to be on the left-hand side, and then there's going to be this component, which is dn multiplied by dn, and then dn will also be on the fraction. So when you work this out, it's going to be a quadratic, okay? And then you're going to get two answers, right? When you do the quadratic formula, you get some answer that's negative and you get some answer that's positive, right? You disregard the negative answer, and the answer that's positive is going to be this one, okay? So you do the same thing, essentially, as before, and you use dn to help you calculate the stiffness, right, using parallel axis theorem shifting, keeping in mind that the tensile steel's modular ratio is n rather than n-1. And the other thing is when you're doing the cracked moment of inertia, keep in mind you want to be using I cracked as BD cubed on 3, okay, rather than 12. That saves you from doing parallel axis theorem shifting for the concrete section. Okay. And that's dn there, and you plug that in right there. Okay, cool. So that gives you the area moment of inertia. Okay, so now the next step requires us to find IEF at all relevant sections. So we know that we only have one relevant section, which is the section at the middle of the beam. And if the moment, yeah, anyway, the beam's cracked, basically. The section's cracked, specifically, right? We found this out in a previous step. Okay, so you see this big-ass formula here, right? This is what I'm saying with, you need to basically learn how to store values on your calculator really well, okay? Because this is a stored value, 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 right? So a lot of the exam, when you're doing it, will come down to speed and not getting tripped up with storing different values and chucking in a big fat fraction, basically, okay? And then not forgetting the squared here. That's another common way to mess it up. Okay, so let's just plug all these things in. Calculate it from previous steps. Okay, someone asked me at the start of this workshop, is this topic hard? And I said, you'll see. But it's hard in like a weird way. It's hard because there's so many steps. It's not hard because any of the individual steps are difficult, I would say. But it's the combination of everything and trying to do it quickly, which is difficult, I would say. Okay, so what you'll find is that M cracked, right, requires you to have it in kilonewton meters because your service moment is in kilonewton meters. Okay, so what do I mean? To calculate this, we basically did like this bending moment diagram analysis, right? And this formula that you plugged in gave you an answer in kilonewton meters, right? When you're doing this ratio, they have to be the same units. And so before we had some huge value, right? Something times 10 to the 6, and we had it in Newton millimeters, right? So you have to make sure that when you're plugging, because it's very easy to make this mistake, basically. You store this value as a value on your calculator and you forget about it, and you divide it by this value, and then you suddenly have an answer that's 10 times 6, 10 to the power of 6, like a factor of that like wrong, I guess. Do you know what I mean? So yeah, just be very careful with that, because that's why you want to store this value in kilonewton meters as well, so that this is compatible with this. Okay. Okay. That gives you an answer when you plug all that in of 2.02, right? Times 10 to the 9. Okay. And then we've got this right-hand side of the equation, and that is dependent on this if statement, basically, right? So it says if PW is less than this, or if PW is greater than this, then do this or this, okay? So PW was actually calculated in a previous step. It was calculated when we were trying to figure out the cracking moment. It's this value here, right? So it's this 0.0063, okay? And we're gonna chuck it into this if statement, basically. And we'll see that it's greater than 0.005, and therefore we're gonna use an IEF max value of just 1 times the gross moment of inertia. Okay, so that's just the same thing as IG. Okay, however, if your reinforcement ratio is too low, the idea is you have to take 0.6 IG as the max. So this max is basically an upper limit of what the stiffness is allowed to be. Okay, but since our stiffness falls under that max value anyway, we don't need to change any numbers around. Okay, so now we find the effective moment of inertia average, which is basically saying you average potentially multiple points along a beam, but for us, we've only got 1 point because we've got a simply supported beam. This will be the case for a cantilever as well, but if I give you an example of a continuous beam, right, what you would do is if you have an end span, like here, and we're analyzing it, okay, there's an end span, you've got some cracks here, and you've got some cracks here. What you would need to do is you would need to take a section here and a section here and analyze them. And then basically you take 50% of the contribution from the middle and the side. And when you add those up, that will be your IEF average, okay? So IEF average is the average between these two section stiffness. Does that make sense? Kind of? Okay. So let me just scroll past that. So on the left there, you can see different cases. That was the case that I was describing. If you have an interior span, you would do that instead. Okay, so the next step and the final step will be determining the deflection. Okay, so for deflection, we're gonna calculate the short-term deflection first. Okay, and so we're going to use a formula basically for if you have a simply supported beam, right? And it follows these two cases, okay? So we have a uniformly distributed load as well as a point load. So these will basically produce two different shapes, and we're going to add them together. Or they're going to produce two different deflection values, and we're going to add them together. So for a UDL, we plug into this formula where beta is equal to 5 on 384, and WS is 15.6 as we calculated earlier. Keep in mind 15.6, we did it as kilonewtons per meter, but you'll see that whether you're doing it in kilonewtons per meter or newtons per millimeter, this is just, when you do this conversion, you're multiplying by 1,000 and you're multiplying by 1,000, but you're doing it on the top and the bottom of the fraction. And so it cancels out anyway. So 15 kilonewtons per meter is actually, in fact, equal to 15 newtons per millimeter, right? So this formula is sensitive to the units that you plug in. So just be very careful. We want an answer in millimeters. And so we should be plugging in everything in terms of mil and newtons and MPa. So with that said, with the length, right, our beam was 6,000 mil, right? Make sure to not plug in 6 meters, otherwise you're going to get the wrong answer. And then your elastic modulus, right, we found it in an earlier step. And then we worked out this in an earlier step, which is IEF average, and this is in millimeters to the power of 4. Okay, so when you compute all that, you'll get that the short-term deflection due to the UDL is 4.81 millimeters, okay? For a point load, the short-term deflection due to a point load, it follows a different beta constant, right? In the case of a point load in the middle, it's 1/48. Okay, here is a very common spot for a mistake. It's where you don't multiply your point load by 1,000, okay? Because we're pretty familiar with using point loads as kilonewtons, right? And so in this particular formula, you need to make sure it's in newtons, otherwise you get the wrong answer. So this has to be multiplied by 10 to the 3 to get it in newtons, otherwise this will be wrong. Okay, and then same thing, 6,000, and these were the same, so I'm not going to rewrite them. This gives 4.33 millimeters, okay? So basically, the short-term deflection is going to be equal to the short-term deflection due to the UDL and the short-term deflection equal to the point load added together. And that will give you 9.14 mil, okay? So, okay. So now we're going to go through a different approach to find the sustained load, to find the sustained deflection, okay? So I'll tell you the logic. So when we were plugging in this formula for deflection, right, it's really annoying, okay? So you have all these things to plug in, right? You've got WS and you got L and you got EI and whatever. And if we had to do that every single time for the short-term load and the sustained load and whatever, it's gonna take forever, right? So our approach is basically saying that, and I'm just gonna delete this real quick. Okay, what we're saying is the sustained load, I'm gonna make this purple. The sustained load, the only thing we actually change is W. Okay, W is going to be replaced by W sus, right? So instead of WS, we use W sus, right? That's literally the only thing that changes. And so instead of re-plugging in every number into this calculation, we're going to find W sus by getting the short-term deflection. You're going to divide out the previous value for the short-term load, and you're going to multiply by the sustained load, right? So we're just doing a ratio, right? We're going to divide out the old loading number and multiply by the new loading number. Does that make sense? So this is like 100 times faster, okay? So that's going to be our formula we use for the sustained deflection. And in order to do this, we need to first figure out the sustained load. Sustained load, there's one for distributed load and there's one for point load. Okay. And it's just, you plug in these values, which we've already kind of, well, we've been given these. And instead of 0.7 for the multiplier for the live load, we're going to do 0.4. Okay. And that's going to give us an answer like so. Okay. So now we have lower values, right, for this sustained load. And so we get the deflection value due to the short-term deflection value due to the UDL and due to the point load. And then we multiply by the new distributed load and divide out the old distributed load. We multiply by the new point load and divide out the old point load. And then we're going to get an answer for our sustained deflection. Okay, bear with me, guys. We've got a bit more to go. And I'll give you a break. Okay. Okay, so creep shrink factor. This is basically a multiplier, and it's based on your how much compressive reinforcement you have relative to your tensile reinforcement. So this number can range between 0.8 and 2. Okay, so these are the lower and upper bounds. And the idea is if you have no compressive steel, if you have no compressive steel, then your KCS factor is going to be 2, right? Whereas if you have the same amount of compressive steel as tensile steel, your KCS factor is going to be 0.8. So the lower number is better because this is an amplification factor for your long-term deflection, right? Okay, so basically if we plug in our values for the area of compressive steel and tensile steel, we get that our creep shrinkage factor is going to be 1.45, right? And basically, to get the long-term load, we get the sustained load, and we multiply it by a KCS factor of 1.45, giving us 11.1 mil of deflection. Okay, and then your total deflection is basically just going to be this value added on to short-term deflection and giving us 20.2 mil. Okay, so yeah, okay, that's basically the end of the question, but normally you would have to basically compare this total deflection that you just calculated against some limit, but in this particular question we aren't asked to do that, and it's not in the solutions. Okay, that's the end of the first question. Here's a different question. Here's a continuous beam, and for this particular question, it asks us to do a preliminary sizing, or basically we had to design the beam based on serviceability. Okay, so it says determine the preliminary size for a rectangular beam shown in the figure, and it carries a superimposed dead load of, so I'll just write this down in the right document. Yeah, a superimposed dead load. Sorry, this was, let's say W dead load SDL, so superimposed, right, of 70 kilonewtons per meter, in addition to its self weight and live load, so WQ, of 50 kilonewtons per meter. The beam is to be used in an office building, so this will tell us about the type, the purpose of it, and it's to have a limit on its span/deflection of 1/350. For durability and fire, the concrete is determined to have 40 MPa, and cover is this, and use this for elastic modulus, and the unit weight of concrete is 25 kilonewtons per meter cubed. Okay, it tells us to use something called the simplified method to compute the bending moments of the members. So this simplified method is referring to the fact that this beam's bending moment diagram is indeterminate, statically indeterminate, and so we can use something called a simplified method, which is in the code, which will allow us to determine what the bending moments are, without needing to use structural analysis methods, basically. Sorry, methods from the course structural analysis. Okay, so step 0, we need to determine how many cross sections which we need to analyze. Okay, so what you can see here is a 3-span continuous beam. 3-span is referring to the fact that the beam has 4 supports and 3 kind of parts to it, and those parts are called spans, right? Okay, and then basically there's 2 types of spans, right? There's an end span and an interior span. So for the end span, you need to analyze 2 cross sections, and for your interior span, you need to analyze 3 cross sections. Okay, so what we need to do is we need to, later when we're doing the average, we need to basically take half the contribution from the middle and from the continuous end for the case of the end span, and then for the case of the interior span, it's 50% from the middle and then 25% from both sides, both of the continuous sides. Okay, so serviceability factored loads, right? We do a slightly different looking formula. Okay, so what you saw before was we were doing WS and W sustained, right? Which looked something like this, right? So G plus phi S, and this one is using phi L, and then multiplying Q, right? So that's what we were doing before. And then later we did W, was it WL? Anyway, so it's used for, this was used to find this, right? Which was then multiplied by KCS to get delta L, which is our long-term load, right? So that was the multiplication factor. So instead of doing all of these intermediate steps, what we can do, which is useful for when we're doing preliminary sizing, is we can just combine all this loading into a total load, right? So this was for delta S, sorry. This was for delta S. This is for delta L. We know that delta total is delta S plus delta L. right? So what we're saying is like, let's make up an imaginary load, right? Which basically tells us the deflection, right? If we were to plug it into that big ass deflection formula, and this load would represent all the creeping effects, etc. Okay, so this is not a real load. This is like a load which gives you the equivalent answer of if you just did elastic analysis for the deflection. Okay, so it's going to be like, what's the word? It's going to be like an amplified load, right? Similar to the way that when you did W star for serviceability, sorry, for strength load combinations, you were using like 1.2G plus 1.5Q, whatever. What this W total load will be is it's going to end up being an amplification factor, similar to this. Whereas in reality, this doesn't represent like the everyday loading, but it represents the equivalent load, which gives you the total deflection. Okay, so that's what this whole thing is, right? Okay, so having said that, oops. This is basically like the formula that we're going to use, all right? We're going to work our way to getting there, okay? So first thing we need to do is basically figure out the self-weight, because remember, in this big-ass formula, we've got WG, and WG has two subcomponents, right? It has the dead load due to the superimposed dead load, and it has the dead load due to the self-weight, okay? So the self-weight component is going to be a function of your concrete's like section size, and we need to design that, right? So we need to do trial depths and trial widths and things like that, right? Okay. And so we need to basically use these tables, which give us a starting point for the depth and the width, right? Okay, but the thing is, right, how do you know what is high loading? Okay, so in this particular question, I might add, okay, so we're told this, right? And since you guys are like undergrad students, right, and not like seasoned like structural designers or whatever, these numbers don't really mean anything, right? Like 70 kilonewtons per meter or 50 kilonewtons per meter, that's like an arbitrary number that they just came up with for the purpose of this question, right? So I want you to think about it more in terms of how big is this number in reality, okay? I want you to think about like physically ground yourself with this number. This is a really, really large number, basically. And why do I know that? It's because this is a linear, it's like kilonewtons per meter, okay? And imagine this beam is a part of a slab and beam system, okay? And you've got a beam here and a beam here and whatever, okay? And let's say we're designing for that beam in the middle, not one of the edge beams, okay? And then we've got columns as well, right? So we've got two directions to think about. We've got the span direction, so span is going like into the page, but for our purposes, we care about the column-to-column spacing, okay? And standard column-to-column spacing is about 6 meters or 8 meters, somewhere in the ballpark of 6 to 8. Let's just say 6, okay? And so they're giving us this load, which is the linear load, right? So W in terms of kilonewtons per meter. What's the kPa load? You know, what was the load when it was a pressure value, right? And we got that through let's call it Q, right, instead of W. Q was W multiplied by that center to center spacing. Let's call that tributary width. Yeah, let's call it trib. Okay, let's just call it trib. Tributary width was about 6, okay? And the value that we got in the end was like, you know, 70 or 50 or whatever. Let's just do 70 for the moment, right? So basically, what I'm trying to say, is that right? No, other way around, sorry, my bad. So W, you know what? This is divided. Okay, so basically where this came from is W was Q multiplied by the trib, right? And so when you rearrange for Q, you get the other way around, right? So basically, if I do this with my calculator, right? You got 70 divided by 6. You're getting a kPa value about 11.6, right? Or 11.7. kPa. Okay, that's really, really heavy. Okay, so here I've got the standards. This is like Australian standards, live loading. And this will basically tell you, right, if you focus here, it says uniformly distributed actions. So this is a kPa load, and it gives you all these different loading cases for various purposes of a building. So if I scroll down to something like areas with possible physical activity, say like a dance hall. So this would maybe be a number that you'd use if you're designing like a club, like a nightclub, and it's like it's on a suspended slab. It's like 5 kPa, okay, for live load. So going back to this, 11 kPa is huge, right? 11 kPa is massive, right? So anyway, it's like a very high amount of loading. So I wouldn't even, like, I don't even know if this would satisfy it, to be honest. But anyway, so this says like 6 kPa, and this is referring to like kind of a Q plus SDL load, I guess. But yeah, anyway, so just take the high loading value basically for this particular scenario. So we've got 2 scenarios. We've got the end span. How's this? So your end span, right, has one end continuous, right? So that's the same thing as this. Your interior span is the same thing as saying both sides of your span are continuous, right? So we're going to take this value and this value. And we're designing the beam, not the slab, okay? So in the question, this end span had 5,000 mil for length, and the interior span had 6,000 mil. So these two numbers are different as well. Okay, so you plug in 5,000 and 6,000, and then you divide by the recommended sizing. Okay. All right, and then when you compute these, you find the maximum between them, which gives you 600 mil. Okay. All right. Preliminary width. So a good trial value for your width is 0.6 of the depth. So we're saying that this concrete section is 600 deep, and so we should take 0.7 of that. Oops. We should take 0.7 of that and have a trial width of 420. Okay, so now we can use this concrete rectangle as our self-weight. Okay, and so we're going to multiply it in terms of the meters. So we'll do 0.6 converting to meters and 0.42. And we're going to multiply this by the unit weight of the concrete. And this will give us our linear self-weight. Okay, so that's 6.3. So you can just see that this number, which is a superimposed dead load, is so much higher than the self-weight. Like, it's crazy, like the number that they selected anyway. So you can now find the linear dead load and the linear live load, which was given.
73.6, not 76.
What did I write? 70.
For the WG value.
70.
Oh no, sorry.
Yeah. I was trying to run through the numbers myself as well. Yeah. Yeah. I see what you're getting at there. I think it's right there. Yeah, no problem. Okay. Let's go to the total load. So again, this total load means nothing in reality, right? Like this is like a fudging kind of formula, right? So this has no like physical meaning, right? This particular distributed load. Okay, so all we do is we're going to plug in values for KCS, phi S, phi L, and WG and WQ, right? So these were the values we just found for the dead and the live load. Okay, but KCS, right? So I kind of skipped this. What we do is let's assume we have no compressive steel when we're doing the trial deflection, like deflection-based beam design, right? Let's just assume we have no compressive steel for the moment, because as soon as we add any compressive steel, it's going to make the deflection better. So we want to kind of design for the worst case scenario first, and then as we add in compressive steel, as we refine our beam design, it's only going to make the deflection better. Okay. So that's why our KCS value was 2, right? So that's as if the beam had no compressive steel in it, giving us this value. Okay. All right. Finding the moment at the section. Okay. So this is multiple values, and so this is the simplified method. I've just like kind of redrawn it to be nicer, like so you can visualize what it says on the standards, right? But the idea is you can basically like approximate the bending moments based on these formulas. Okay. So for the case of the end span, the bending moment in the middle is a positive value, right? So you have sagging, and it's equal to WL squared on 11, and that L, by the way, is the span of just the end span. Okay. And for the continuous moment, right? Sorry, the moment at the support for the end span, make sure it's a negative number because you'll get like a negative bending moment at that location, right? And then for interior span, the length is longer. So this was 6 meters instead of 5 meters over here. And then yeah, at the supports, remember these are negative and the middle should be positive, right? For the bending moment. So you can just get all those numbers through a simplified formula, which is really nice. Okay, so when you're doing my preliminary size step-by-step method thing, you basically skip to step 4. So you go from step 1 to 4. And we're going to go to this now, the IEF average formula, okay? So what this is for the case of a single span, right? Remember you had a formula that looks something like this, right? This was for a simply supported case with a uniformly distributed load on it. It looks something like that. And this is, this loading scenario, right? For a continuous beam, we can use a approximation, right? Based on this formula. Also, what this formula does is it moves I onto the left-hand side and it moves the deflection onto the right-hand side. Okay, so it's going to look a little different, but it follows this formula and it's saying that IF average should be bigger than this number, okay, that you work out here, okay? And what you'll also notice is that instead of L to the power of 4, they changed the L to the power of 2, and the reason for that is because you're multiplying by the moment, right? And the moment will have like WL 2 on 8, something, right? So the L is like a part of the M formulation, right? Okay. Anyway, so for the end span, we know the end span is 5,000 mil, whereas the interior span was 6,000 mil. We know what the elastic modulus of the concrete was. So the deflection, right? When I said we move the deflection onto this side, what we're actually plugging in is the limit of deflection, right? And the limit of deflection is the span, or L, over some number. And the question told us it was over 350. Okay, so what we're actually plugging in is L on 350. So we're going to plug in L again here. And then here it's going to be 6,000 instead, right? Okay, so now we plug in all of those bending moments we found from using the simplified method. So the mid-span deflection should be positive, right? Whereas the ones for the supports should be negative. So when you're adding here, you're actually subtracting because of how this formula works, right? And you're also not subtracting the left-hand side for the case of an end span, or I shouldn't say the left-hand side, the span that's not continuous. Okay, and so that gives us IEF average, right? In both cases, right? I'll just plug in the rest of the numbers. These two are the same, so you can also do this multiplied by 0.2 if you want instead. Okay, so now we have IEF average for the end span case and for the interior span case. So as you can see based on these numbers, the end span case is actually higher. It's saying that our moment of inertia has to be bigger than this number, right? So the idea is you take the maximum because it has to be bigger than both these numbers, and therefore it should be bigger than the biggest number between the two. Okay. All right, and then basically this is the note from the lecture slides. It says that we can determine the total deflection using the following approximation. So what we say is IEF average, how IEF average is related to the stiffness, right? So IEF average is like factoring in all these things like cracking, right? Whereas we just want to figure out the depth, right? We want to like refine the depth of our section. And so we're kind of going off of IG, which is BD cubed on 12. So it's like, how is BD cubed on 12, or rather the depth component specifically, related to the cracked section stiffness, right? And it's through this factor of 0.4 as an approximation. So just keeping the same like cross-section ratio in mind of 0.7, we're going to be able to get this formula. Oh, I'm missing a 4 there. Oops. We're going to be able to get this formula, which looks like this. Okay. So keep in mind this is 4 because we've got depth and we've got depth to the power of 3. And so when we don't do a square root, we don't do a cube root, we do a quartic root, right? So it's going to be when you type it in your calculator, it will be square rooted with a 4 here, basically, right? Okay. And so we plug in the IEF average value that was the maximum between those two, and it gives us this. So it's basically telling us the depth that you select has to be greater than 632, right? Assuming a ratio of 0.7, right? So it's like saying this, right? This is the minimum depth that's allowed, right? Whereas the minimum width was 0.7 times that. Okay. What we did is we selected 600 as our depth. So you can tell that it's already too low, right? Which makes sense considering how high the loads were and the fact that the table only really went up to 6 kPa rather than the really, really high number we had before, like 18 or something. So it makes sense that like we kind of undershot it. So instead we need to select a new number. So we just make this beam bigger, right? So we go to 650, like so. And we just, instead of taking that, we just set it as like a fixed value of 450 for the width, okay? The idea is the new dead load is not very different. So this is due to the self-weight. It's not very different to our dead load that we did the analysis with, because the contribution of the self-weight versus the superimposed dead load was pretty minor anyway. And so we don't need to do like another iteration, okay? Because it's not going to change that deflection by much. And also we overshot the depth, the minimum depth by a bit anyway, okay? All right, so that's pretty much the 2 questions I want to go through today. What I'll show you as well is the remaining pages is to do with one-way slab design, okay? And I'll show you what's on the pages, right? There it is. The idea is when you have a slab, right, there's 2 things that determine whether it's a one-way slab or a two-way slab. The first thing is whether there's beams underneath it, all right? So for example, here you've got a one-way slab, whereas here you got a two-way slab. Okay, so you have beams that break up these like individual rectangles, right? So this is from top-down view. And if you have how do you say this? When you have beams that form like this kind of almost square shape, right? In terms of these bays, how the forces want to distribute is into the beams like so. Okay. Whereas for the case of a one-way slab, the forces go in one direction, so from the slab to the beam. even if you have these edge beams, this is still a one-way slab, and the other reason is because of the aspect ratio. Okay, so if this is really long and skinny, right? So let's call that Ly, and let's call it Lx. If Ly to Lx is greater than 2, it's a one-way slab. Okay, so when you have a greater than 2 to 1 ratio of your length in that direction to your length in that direction, is a one-way slab. So that's a one-way slab, and then one-way slabs are a part of your course. Two-way slabs are not in the scope of the course. Two-way slabs are reserved for advanced concrete if you decide to go on and do that. And you just have to do these checks basically, right? And you'll do flexural design, which is from week 5 and 7. You'll do shear design, which is from week 8, which is last week, and you'll do serviceability design. So these 3 kind of checks and types of design checks is all included in slabs, right? The main thing is that this is basically just a really wide beam, because we design a slab to basically be a 1,000 millimeter width beam, right? And generally the depth is a lot lower, okay? And then you've got reinforcement running in 2 directions, and no stirrups, so no shear bars, nothing like that. Okay, that's reserved for beams. Yeah, so you can have a look through these notes yourself and follow through, and this is like a full slab design. And there's also a little bit at the end for incremental deflection, which is a specific type of deflection criteria. Okay, all good. Good luck for your studies.